Hello guys, Sir DV here. So this is our first lecture in structural dynamics. So in this particular video I will discuss the basic principles of vibration applicable to SDOF systems. So basically the theory of vibration is founded on the analysis of a spring mass damper system, and the consideration of the single degree of freedom system is significant, no, for us to understand its application to multi-degree of freedom system. So what is a single degree of freedom system or SDOF system? So an SDOF system, which is modeled in terms of a mass spring or damper system, may be modeled. Okay, so in terms of this figure here drawn in this presentation. So if we consider a motion of such a system in the direction of the coordinate y, so a single degree of freedom system simply represents a movement along this direction. That's why it's called a single degree of freedom. So the degree of motion or the direction of motion is actually limited to only one direction, which is coming to and positive and the negative direction of this y coordinate or this y axis. And this motion is actually defined in terms of the relationship between these three variables, no? Whether a fourth variable is present or not, with or without the presence of this force that will make this system move along this direction, the mass spring damper system is still a complete system that we may consider in the analysis of this type of vibration. And the differential equation of motion of such a phenomenon or system may be derived by using the basic laws of mechanics or physics, upon which a reverse effective force equivalent to the mass times the acceleration given by this term here. Okay, so this term here, my double prime, is actually the inertia force that we have studied in our dynamics, not the principles of dynamics. So this inertia force is simply the reverse effective force or the D'Alembert force that will balance the the system into what you call a dynamic equilibrium, not to mention the other forces that are present in the spring, in the damper, and the applied force. So the nomenclature, the parameters are defined here in terms of these variables, and to understand better this equation, we can simply sum up all the forces along the along the y axis is equal to 0. Everything going to the right is defined in terms of this force, and everything going to the left are defined in terms of these forces. Okay, so there are 4 types of vibration to consider here in our system, and we will tackle them one by one. So the first type is the free undamped system of vibration. So in the free undamped system, we now consider your force P as a function of time be equivalent to 0. Since we are now in dynamics, we have to be accustomed to using variables in terms of the function of time, whether the time is related to the function or not. In general, the system is actually time dependent. So another thing in the undamped vibration is such that your Cy prime is equal to 0, where Cy prime is actually the force that the damper exerts on the system itself, where y prime is the velocity. If we differentiate the variable y dy with respect to dt in terms of function of time, so this is actually a velocity. So if we multiply the velocity by the damping coefficient, okay, so the coefficient of damping, then we now have a damping force. But unfortunately, in the free undamped vibration, again, as I've said, this is equivalent to 0. So your general equation for motion now becomes my double prime plus ky equals 0, which is a very simple differential equation to solve, upon which the basic solution can only be derived, may be derived rather, by simply considering a characteristic equation in the form of the differential operator d squared plus omega squared is equal to 0. So notice that the double derivative there is actually related to a second degree operator, while if there's no derivative, this actually represents a unity, no? So simply it's simply a d squared plus omega squared times unity is equal to omega squared, and this is equivalent to 0. And this is not difficult to solve, since your d is simply the square root, okay, of a negative number. So d is simply the square root of a negative omega squared, and we know that the square root of a negative 1 is simply an imaginary number. Hence your resulting root for this equation is simply a plus or minus I omega. Okay, So for the general solution here, when the root is an imaginary root, okay, or a complex root is imaginary, then your solution is in the form of a trigonometric sine and cosine. Of course, the other solution may be in terms of an exponential solution, but it's easier to solve a trigonometric solution, so we opt to choose a trigonometric solution here, which is simply yt is equal to a cosine of whatever the coefficient of the imaginary root has, omega t, plus b sine, again the coefficient of the imaginary root, omega t, will be the general solution of this equation. So general solution simply states that your constants a and b are yet to be determined by using boundary conditions. So to convert this into a particular solution, or a not a particular but a complete solution. Now we simply apply the boundary conditions. So the boundary conditions are the conditions upon which your initial time t at 0 specifies what's happening in the boundary. Okay, so in the initial condition, if we assume at time t equals 0, okay, so your time t now here is 0. If we assume that at time t equals 0, the boundary, okay, behaves in such a manner that the displacement is equivalent to a fixed value yo, and the velocity is equivalent to a fixed value v sub o, then we can find a and b by simply substituting this into the equation. But of course, if we are looking into the velocity equation, so this is in terms of velocity, we simply differentiate your y with respect to time, so this will be the result, and this is now your displacement equation. Okay, so substituting at y equals 0 the value of yo and vo here, and this becomes a cosine of 0, the sine of 0, sine of 0, cosine of 0, then a and b will yield these values here. So I will not show you how it is done, so please just try it as an exercise at home to solve for a and b using simple algebra. Okay, so the solution now becomes, the complete solution now becomes yt is equal to yo cosine omega t plus vo over omega sine omega t, where in omega becomes now a significant variable that would represent the angular frequency of vibration in radians per second, and it can be converted simply into a frequency, angular frequency of vibration in cycle per second, by simply using this formula. No? So we take note that 1 cycle per second is simply equivalent to hertz. Okay, so this is the unit that is commonly used when we are talking of frequency. Okay, so how did this formula came into existence? So this is just a matter of converting an angular frequency in terms of a rotational frequency. We know that um, if we multiply if we have omega in terms of radians per second, and I want it to be converted, okay, so radians per second, and I want it to be converted into cycles per second, then we know that this is 2 pi radians is simply equal to 1 cycle. Okay, so this will cancel there, so this is simply W over 2 pi. So this is now in cycles per second. So this is now the formula if we want to get the angular frequency in terms of hertz, or frequency in hertz. Okay, to extend the definition of your angular frequency, we know for a fact that rotational motion is repetitive, no? So if we have a rotating point, so we are actually making use of a repetition, such that the wave, no, if we are going to start with this, so this simply is actually can be represented by a wave, no? So this circular motion can be represented by this wave, such that we have one cycle or one period of wave coming from here to here. So this, the circle starts here and ends here, so that's one cycle. So that we ought to take note that this one cycle, which represents one circular motion, is simply repeating, no, in nature. So we take note now that the sine, okay, of such an angle here, whatever is this angle here, omega, okay, will simply be equivalent to a series, no, of values which are the same if we are just adding a cycle. Let's say omega t plus 2 pi, the sine is simply equal to the sine of omega t, okay, while the cosine of omega t plus 2 pi is also equivalent to the cosine of omega t. Okay, so if we are now dealing with angular values, then we say that omega t plus 2 pi is simply equivalent to omega t plus 2 pi over omega. So I just factored out omega here to represent a period, to define a period which is simply this value here. So this now represents your period t, which is what? Repeating and repeating until such time that this circular motion ceases. Hence, this t here, which is equivalent to 2 pi over omega, is simply called the period of vibration. And you will notice that this is simply the reciprocal of your frequency here. So 1 over f. Why? Because your frequency is omega over 2 pi, and your period is 2 pi over omega. Okay, so the frequency and the period are just reciprocals. So that ends the first type of vibration, free and damped. In the second, in the succeeding video, I will discuss to you the free damped vibration, to discuss some mathematical preliminaries in differential equation, since the inclusion of a damping force will create some difficulty in the solution of your DEM. So thank you very much, and I'll see you in the next video.